A good friend of mine, Jack Baker, doing a talk called Wine for Video Game Hackers. So give him a warm round of applause.
Good friend. All right. Thank you for that. Thank you for pretending I'm a good friend. Yeah, hi. My name's Jack Baker. I'm going to be talking about video game hacking. Let's just get through the boring stuff real quick. So like I said, my name's Jack. In my professional career, I am the game security lead for a moderately popular online game. I'm not speaking on behalf of my employer, though. Please don't dox me. So what are we talking about? You're going to be hearing the term wine a lot. So we'll probably talk about what is wine, what does that mean, how does it work, so a little bit about video game hacking basics, using wine to bypass common cheat detections in video game hacking, and then the flip side of that, detecting cheats that are running under wine. So first off, what is wine? You'll probably hear this described in a few different ways. The way that I like to describe it is wine is essentially a compatibility layer for Windows on Unix systems. Maybe the simpler term would be wine lets you run Windows applications on Linux. The most common use case here is video games. You can do other things. People don't typically do that. It's mostly video games. So who cares about this? Well, for years, wine was sort of a niche without direct support from developers. There was so few people trying to play video games on Linux that if it didn't work, you're on your own. This changed pretty significantly in the last few years because of a lot of support from Valve, the company behind Steam, who made a big investment into Linux gaming for their Linux distribution SteamOS and more recently the Steam Deck. Wine is actually the core technology that's underpinning Valve's Proton, which is a suite of all sorts of software that allows you to run video games on Linux using Wine really as the core component. So to simplify, if you own a Steam Deck or for some reason you use SteamOS, you're already using Wine. That's how games work on those platforms. And so what this means is that developers suddenly have to care about wine compatibility because there's actually an audience there. It's no longer a niche. And this has changed the landscape for cheat detection pretty significantly and in ways that, in my opinion, neither cheaters nor anti-cheat engineers have really fully caught up with. And so we'll get into that. But first, let's talk about how wine actually works. And sort of a hint for this is in the name. So wine is a recursive acronym. It means wine is not an emulator. So what that means is the way wine does not work is it's not virtual machines, it's not containers, it's not emulation, anything like that. In fact, when you use wine to play a Windows game on Linux, you're not actually using any Microsoft code at all. And what's interesting is wine runs Windows applications basically like they were native applications on Linux. And it uses a lot of novel stuff to do that. Getting into wine internals, we can basically break wine down into two components. We're oversimplifying a little bit, but for our purposes, it's good enough. The first is executable loading, and the second is basically what I'll call a simulated Windows environment. So the first part of that is executable loading. Some of this you're already going to know, bear with me. But the native executable format for Windows, your EXEs, your DLLs, etc., is called a portable executable, or a PE file. Linux, obviously, doesn't have native support for this format. So the first thing Wine has to do is basically parse PE files and be able to map them into memory more or less the same way that the operating system already does with ELF files, the native binary format of Unix systems. There's a lot that goes into this, but it's not super interesting. The PE file format is pretty well understood. You can probably sort of imagine how this works. So let's talk about the more interesting aspect of Wine, which is what we'll call the simulated Windows environment. Wine defines things, what we call prefixes, which basically is a separate instance of Wine, kind of like a separate container where everything is confined within as one segregation of the operating system. Each prefix has its own file system simulating a real Windows file system. And you can run processes in separate prefixes at the same time. So you can have almost like different instances of Windows running at once. So we've talked about executable loading, but just loading a PE file into memory isn't enough to actually run that on Linux unless it's really simple and you never actually call any Windows libraries or anything like that, which obviously doesn't happen very often. The majority of work that goes into the development of Wine is basically re-implementing Windows standard libraries for Linux. So to give an example there, let's say you have an application and you call create file W, the standard way to create a file, which is a function defined in kernel32.dll. Rather than actually using Microsoft's official kernel32.dll, what Wine has is a custom-built version of that DLL that just translates those function calls into something that can be handled by Linux. So let's use like a really simple example, the simplest thing I could think of, which is handling virtual alloc and virtual free as if they were Windows function calls. And we choose these because they're pretty easily to parallel with the libc functions malloc and free. Virtual alloc and malloc used to allocate some amount of space on the heap, and virtual free and free used to deallocate that space. So if we wanted to do like a really simple implementation of translating these function calls, we could just do something really simple like this. I hope that's readable enough. But basically, we define virtual alloc, and we just translate that call into a roughly equivalent call to malloc, and we do the same thing with free. This is way oversimplified because both the Windows functions have a lot more options that you could use, but this is close enough to tell us what Wine is basically doing. It's taking those calls to Windows standard libraries and translating them into calls that Linux is able to understand. While you're looking at this, you might be wondering, doesn't this whole process fail if an application issues a syscall? And if you're not wondering that, and you have no idea what I'm talking about, a syscall is essentially a way through which an application can directly interface with the kernel of whatever system it's running on. And since Wine doesn't do emulation, we don't actually have a Windows kernel available. How does this work? So to answer this, we need to sort of compare how Windows and Linux treat syscalls. So on Linux, or really any Unix system, applications can and relatively often do directly issue syscalls because the syscall table, the structure that defines what a syscall is, what its number is on this table, what its arguments are, what it does, it's well documented and it's consistent. It doesn't break between versions. It's always backwards compatible. So if you were to go about and try to build something like Wine for Linux applications instead of Windows applications, you'd run into issues anytime an application issues a direct syscall because you're not emulating the kernel, so you can't really handle that accurately. The story is a bit different on Windows. So Microsoft states that the Windows syscall table may change at any time. And in fact, between major releases of Windows, it does change in ways that break backwards compatibility very often. So as a result, Windows applications virtually never issue direct syscalls because it's just not reliable. Instead, what they do is they just call a standard library function, and that function does the syscalling for you. So rather than having the syscall done in your application, you let the standard libraries do it. And since those standard libraries come directly from Microsoft, they're always up to date with the correct syscall table. You don't have to worry about compatibility. What this means is Wine doesn't need to do syscall emulation or syscall interception because applications just don't do syscalls in Windows typically. Now, I will say, just for completion's sake, there is a little bit of an exception to this, which is that some versions of Wine, particularly that in use by Proton, actually are capable of some small amount of syscall interception using what's called a seccomp filter. So seccomp is a feature of the Unix kernel that allows a user mode application to modify the way that the kernel will handle syscalls from that application. However, this is super limited because it's specifically designed to handle the needs of a few applications that actually do issue direct syscalls. This is for the most part things like DRM platforms or game anti-cheats that try to do weird things with the low-level operating system. So for the most part, we can ignore this, but it'll come up again later. Anyway, so talking about how does Wine work, if we're able to load PE files into memory and we have a simulation of the Windows runtime, we basically have all the ingredients we need to run Windows applications on Linux. There is one thing that we've sort of alluded to, but we haven't directly discussed here. Because Windows does not do kernel emulation because Wine does not do kernel emulation at all, you do not support Windows drivers within Wine, full stop. So that will also come up a couple times here. But seriously, who cares about any of this? Well, the reason that we talk about this is because now that we understand how Wine works, we can talk about why it matters, which is that Wine creates a whole bunch of new possibilities when we're talking about video game hacking. So just to level set things just a little bit when we talk about video game hacking, as opposed to, exploiting web applications or things like that, the goal with video game hacking is typically just modification of the application on your local system. It's not reaching out to APIs and things like that. You really just want to make the local application running on your computer do something different than it usually would do. And so we have sort of a catch-all term, which is an anti-cheat, which are systems that attempt to either detect or prevent local modifications to the game. So when we talk about hacking, we're specifically talking about what you might also call just modding, basically trying to modify an application at runtime on your system. And so when we talk about anti-cheats, we can break that down into basically two categories. You've got user mode and kernel mode. And so let's start with user mode cheat detection. So we know Wine is not an emulator. I'm going to throw in another rule and say Wine is also not a sandbox. It doesn't prevent Windows applications from accessing the Linux environment, and it also doesn't prevent Linux processes or the Linux environment from interacting with Windows applications. So what that means is if your anti-cheat system doesn't account for Wine users, it's probably ignoring the existence of the entire Linux environment that's running within those systems. So again, let's use the simplest example we can think of to demonstrate this, which would be checking for debuggers. This is like baby's first anti-cheat detection is, am I being debugged? And for this, we'll use the Windows standard library function isDebuggerPresent, which does exactly what the name suggests. It detects whether or not a debugger is attached to the current process. So for this, we're going to use some pretty simple code. We're basically just going to check every second, call isDebuggerPresent, and then print out the output of that, just to be able to see, are we currently being debugged or no? And so if you do this on Windows, it works exactly how you would expect. But when you do it in Wine, you see something kind of interesting. So if you run your application in Wine, and then you run a debugger also in Wine, let's say WinDebug running in Wine, and you attach that to the program, it accurately says, yeah, I'm being debugged, something's wrong. But again, Wine processes are just Linux processes with some fancy stuff going on. So what happens if we attach a Linux debugger? We attach GDB from sort of the host operating system. Well, in this case, the program has no idea what's going on. isDebuggerPresent doesn't handle this, and we can debug the process however we want, and it'll have no idea that it's going on. But like I said, this is like the very first thing you would try as an anti-cheat developer. So let's talk about something a little bit more complicated, and that's going to be runtime memory inspection. So when you're trying to modify some game, one of the more common things you do is you allocate some space and you put your own code in there. You insert new code into the game to do whatever it is you're trying to do. And so a very common anti-cheat detection is to just look for code in your process that shouldn't be there. In this case, it could be code injected by a hacker, or it could even be just the Wine internal libraries, which also get loaded sort of externally from your application. So in this case, the code's a little bit more complicated. But basically what we're going to do is we're just going to iterate through all of memory, starting at address 0. And we're going to query everything using this Windows standard library function that's called virtual query, which just says, tell me everything you know about a specific block of memory. Is it allocated? How is it allocated? How large is it? Etc. And so if you use virtual query on a block of memory that is not allocated at all, what you'll see is that the state of this memory is this value mem_free, and the protect value is page no access. This means that if you tried to access that memory, you would get an exception because there's nothing there. It's unmapped memory. This works fine on Windows, but again, you get weird results when you do this on Wine. The interesting thing is that memory pages that are allocated by the Windows environment, like in the Wine application itself, they are visible to virtual query or its partner virtual query X, but memory pages that are allocated by the Linux environment are not. And in fact, if you call virtual query on this, it'll treat it like it's an unmapped memory page. It'll say, this is free, it's inaccessible, and it's kind of a lie because you can access that memory. You can read it, you can execute it, it's there. Virtual query is just telling you the wrong thing. And so what this means is we can inject code into our Wine process, and if we do it via the Linux environment, it's really difficult to detect it's there. Like you're essentially, the APIs that are designed to do this will just sort of lie to you, which is fun. Let's put aside user mode cheat detection for a bit and talk about kernel mode cheat detection. So the anti-cheats in this day and age that you're most likely to encounter aren't user mode anymore. They are kernel drivers that are running, high level in your operating system in order to watch everything you do. And so Wine does not support Windows drivers, as we've talked about. And for a long time, this just meant that any game with a kernel level anti-cheat, you just couldn't play. So sorry, Steam Deck users, no Fortnite or anything like that. But because the population of people playing games under Wine has grown so much, that's no longer a tenable solution, and these anti-cheats have had to sort of adapt. And what this means is that those anti-cheats that do support Wine have to work without a kernel driver, which puts a cheater at a big advantage. Because the whole reason that anti-cheats moved into the kernel was, one, it gave them better visibility into the operating system, and two, cheats had already moved into the kernel, and it was the only way to really keep up with them. This sort of running in Wine sort of puts the attacker at an advantage where they can execute from within the kernel, and the defender, the anti-cheat developer, doesn't have that same capability. This does get a little bit more application specific. I don't really want to talk about specifically what does BattleEye do or things like that. So I want to get more into the general ways of cheat detection from there. But this does create an interesting opportunity, which is that if you can convince the anti-cheat that you're running Wine, even though you're on legit Windows, you can play that game without its kernel driver. I don't know how many people are really trying to do this, but it's an interesting thought that I don't know if has been totally considered. Anyway, so I sold my soul. I now work in anti-cheat development as opposed to being a game hacker anymore. So let's talk about the other side of this, which is Wine for anti-cheat developers. So if you're trying to detect cheats using Wine, the first thing you need to do, and really the key to being able to do anything at all, is detect the environment in use. Are you on Wine or are you on legit Windows? And so just to clarify, platforms don't typically support separate builds for Wine versus Windows. It's just one build that everybody, whether they're using Wine or Windows, gets. So we need to do this detection at runtime. And so just to level set things again, why do we care about this? Well, if we mistake Wine for Windows, we end up ignoring the existence of this entire Linux environment that can be used to exploit our system. And if we mistake Windows for Wine and we're trying to do kernel level protections, then those just aren't going to work because we know that that kernel driver isn't going to work within Wine. So let's talk about ways that we can detect the platform at runtime. The simplest way, and the way that most applications do it, is they just ask Steam for it. Steam has this utility function, is Steam running on Steam Deck? And despite the kind of misleading name, this is not just Steam Deck, this is Steam OS. Really, any environment that includes Wine, this will detect. But because this is just a function within a third-party library, this is trivial to bypass. You just hook the function, modify the library, whatever you need to do to make it lie. So this is not a reliable method at all. Let's talk about a few more examples of things that are just a little bit more complicated. So if we wanted to look for ways that we could check for Wine versus Windows, we could look for hardware IDs. This might work a little bit better on, say, Steam Deck than somebody's desktop running Steam OS. Wine prefixes include what's called the Z drive, which is directly mapped to the host Linux operating system. So the existence of this could be an indication that you're running on Wine. There's at least some possibility of false positives if someone just happens to be using that drive letter. And there's probably a dozen other simple examples, but let's talk about something a little more complex and a little harder to defeat. So let's try to identify our platform just by looking at inconsistencies in the environment. Obviously, Wine and Windows are different code written by different people. There are places where they're not going to match up. So we could do this in a couple ways. The first is we could find functions that behave differently in Wine. They take different arguments, or they just don't do the right thing. Or we could just find functions that don't exist at all in Wine. And we're going to do the second one because it's a little bit easier. So Windows has a whole ton of undocumented functions in various system libraries. Some of these aren't implemented in Wine because there's just no need for it. Nobody's using them. So just one example I found off the top of my head was this nt-set default hard error port. I don't know what that means. Doesn't matter. All we know is that it doesn't exist in Wine, and it does in legit versions of ntdll.dll, which is the library in which it's implemented. And so we can do this really easily. We're just going to get a module handle to ntdll.dll, and then we're going to call getProcAddress, which is just a function that says, find me the address of this function within this module. We give it that name, and if we're on Windows, we're going to get some non-zero value because that function exists, and if we're on Wine, we're going to get 0 because that function doesn't exist. And just like that, we can tell pretty easily whether or not we're on legit Windows or Wine. But we can make this more complicated. Let's talk some more about syscalls. Like we've said before, Wine does virtually no syscall emulation or interception. There's one real exception, and if we ignore that, what happens if we do issue syscalls? Well, these syscalls, instead of going to the Windows kernel like they would be expected to, they go to the Linux kernel. What that means is we can make Linux syscalls from a Windows process. And just as a quick aside, something that's really kind of interesting about this is, let's say you're doing a CTF or something and you're exploiting some binary that is a Windows application running in Wine. If you're using like Metasploit or something, that means that you can actually use the Linux payload or the Windows payload. They will both work, which is super weird. But it makes sense in the context. Anyway, getting back to it, let's construct a syscall that we can use to identify what platform we're on. But first, just for the sake of completion, let's remember that Proton does have a seccomp filter that does intercept syscalls. And so on its own, that would be a problem that would get in our way from talking directly to the Linux kernel. But this is just a compatibility filter. It's not an actual security control. So it's pretty easy to bypass. So to start with that, we can bypass the Proton seccomp filter in a few ways. The first is we just issue the syscall from i386 mode, so like 32-bit mode as opposed to 64-bit mode. We can issue the syscall from a memory address that's reserved for what's called Wine64 preloader. That's anything in this range. Or we can just issue the syscall from any memory address greater than this big number. We'll use the third option since it's the easiest. But so basically, here's our code to do that. It's a little bit complicated, so let's break it down. The first things first, we've got an assembly payload, and all it's going to do is it's going to take our arguments from a C function, translate them into the arguments for syscall. It'll issue that syscall, and it'll return the value. So what this means is we can make syscalls basically as in the form of a C function call. Then what we're going to do is we're just going to allocate a page of memory at that really big address that we asked for. We copy our syscall payload to that, and then we call virtual protect to make that memory executable so that we've basically created our syscall function at that address. Now that we have sort of our harness for making syscalls on the Linux host environment, let's make a syscall that we can use to identify which environment we're on. So there's countless ways we can do this, and again, I'm just going to do the simplest one I could come up with. So what we're going to do is we're going to issue syscall 0. And so this is going to depend on which environment you're on, but on Linux, 0 refers to the read syscall, whereas on Windows, this is going to vary depending on which version of Windows you're on. But let's call it NT access check because that's what it would be on the most recent most recent Windows kernel. And then we issue this syscall with all zeros as arguments. On Linux, that's a perfectly valid syscall that we've made. We've asked the kernel to read 0 bytes from file descriptor 0, which is standard in. That's completely allowed, and it says, great, that worked perfectly. Here's your 0 bytes. And on Windows, we just gave it a bunch of incomprehensible bullshit, so it's just going to give us an error code instead. So based on the return value of the syscall, we can tell which environment we're on. And so this is super simple. We just issue our syscall a bunch of zeros and say, did we get that error code? Yes, we're on Windows. No, we're on Wine. Simple as that. But so we can use syscalls for a lot more than just identifying the environment. We can effectively do anything on Linux that you would be able to do as the Linux user. So Wine is not a sandbox. This isn't a security control. But if it was, we would have broken out of that sandbox at this point. So let's go through our earlier examples of cheat detections and see how we can detect them now that we have the ability to issue Linux syscalls. So the first thing we talked about was checking for debuggers. Let's put together something where we can detect a debugger regardless of whether it's happening from the Windows environment or from Linux. And so to use this, we'll use syscalls and we'll specifically use the ptrace API. So this is a fair amount more complicated code than last time we looked at checking debuggers. But the first thing we're going to do is we're going to issue the get PID syscall to get the process ID on Linux, not the Windows process ID, for our current process. And then once we have that process ID, what we're going to do is we're going to fork. We're going to create a child process with the same state as our current process, and we're going to use that child process to try to attach a debugger to the parent process whose PID we just learned. And this could have two results. It could succeed or it could fail. And if it fails, the most likely explanation is it failed because there's already a debugger attached to our process, and you can't have more than one. So based on the output of this syscall, the ptrace attach syscall, we can tell whether or not we're being debugged. And this will work regardless of whether or not the debugger is in Windows or in Linux. It's, so we've bypassed that restriction there. Now the other thing we talked about was runtime memory inspection. What we want to do is look for unexpected memory allocations in our target process. And the way that you typically would do something like that on Linux is you would look at the file proc self maps, which is a special purpose file that contains a text-based list of all the memory mappings in your current process. And up until last night, I had a whole bunch of code on this slide of how you would do that using syscalls. Then I realized you're being stupid. You don't have to do any of that because you have the Z drive, which will just let you read things from the Linux file system. So you don't need syscalls for this part at all. All you need to do is read Z proc self maps, and you can read the real canonical memory mappings of your process from your Windows environment. Okay, so in summary, what we've noticed is that Wine breaks most user mode cheat detections in one way or another. If you're trying to detect cheats with just the Windows environment in mind, Wine is gonna break that whole process. We can adapt to this as long as we know the environment we're running in. This is really the key to that. If you don't know your environment, you have no way of meaningfully adapting to these kinds of new cheats from within Wine. And kernel mode is still a really big missing piece for anti-cheat on Wine. There is no equivalent for what is possible on Windows right now. And this is great news for hackers because it gives you a big advantage that has been missing for a number of years now. So as far as future work, we've talked about environment spoofing, but it's mostly been in the context of making Wine look like legit Windows. I think there is some utility in doing the exact opposite. Running on legit Windows and trying to make it look like you are running in Wine. Specifically because that means that you're going to cause the anti-cheat system to assume it can't run with its kernel driver and put itself at a disadvantage, essentially. Another way you might go about this is just, well, what if you could compile Wine and run it on Windows? This has been attempted. It's not as easy as it sounds, but I think it would be quite interesting for this type of thing. Also for future work, I think it's really interesting to think of where do kernel anti-cheats go from here. So technically, if you wanted to be like really especially unethical, you could just sort of like try to root someone's Steam Deck by using syscalls on the Linux environment. It's not really designed to prevent that, but I do think that would be a big step past what I think is really acceptable for users at this point. So I'm curious to see if kernel anti-cheats take that step and try to put kernel drivers in the Linux environment, as opposed to just sort of sticking with Windows as they have so far. I don't know if platforms will allow this. That's really the big question. And yeah, I think that's it for me. Any questions for anyone? Yes. I'm sorry, what? Okay, so the question is, have we tried this on FreeBSD or any BSD systems? I have not, but I can't imagine it would be significantly different, primarily because, Wine works the same way on those systems. I think if anything were to be missing here, it would be the seccomp filter, and that would essentially make your life easier. Cool. Oh, yeah. Oh, that's interesting. So the question is, correct me if I heard you incorrectly, but has .NET 4 running on Linux made a significant difference? So I would have to think about specific examples where, as opposed to running in the Wine environment, games are like making specifically .NET builds for Linux. I can't think of examples. I think for the most part, games get by just by having this not simulated Windows environment, which can include .NET like sort of natively within it. So I can't think of examples where that is the easiest route to getting something to run on Linux, I guess. All right. Well, thank you, everyone.